Ada, Countess of Lovelace, came from an aristocratic family. Her father was Lord Byron. He was an active member of the House of Lords with surprisingly liberal views for his time. He was also, of course, one of England's finest poets. He became an iconic figure in the Romantic movement, and after Shakespeare, he was, and still is, the best known of the English poets abroad. And he might be said to have invented the cult of celebrity. He really was the first.
To blame him for something.
Ada's mother was a highly intelligent and well-educated woman of high moral principles, who was prominent in the prison reform and anti-slavery movements. We have here a painting of the World Anti-Slavery Convention in 1840, and she is there, I think, somewhere just about there, which is quite something. Ada herself, and I got what I think is the nicest portrait of her, and it's actually done by a female painter as well, Margaret Carpenter. Ada received an excellent education, both in the classics and the sciences. As a young woman, she regularly attended court, and she mixed in society and in intellectual circles. She married Baron William King, who subsequently became the Earl of Lovelace, which is where she gets her title Countess of Lovelace from. And that's her husband, who you see far outlived her. His main claim to fame was that from 1840 until his death in 1893, he was the Lord Lieutenant of Surrey. Think of that, which you very wish. Ada had 3 children by him, and in her will she asked to be buried next to her father. So, let me start all over again. Ada came from a broken home. Her father, himself from a dysfunctional family, was a drunkard, a spendthrift, and a sexual predator. He had children by a number of high-born women, including his half-sister, but his preference was for teenage boys. Ada's mother left him shortly after Ada was born on account of his behaviour, and about 3 months later he left England for good to go to live in Italy, where he could more easily indulge his sexual preferences. He died when Ada was 8. Had he lived to see her as a mature woman, he would most certainly have disapproved of her. He wrote in his satirical epic poem, Don Juan, "'Tis pity learned virgins ever wed with persons of no sort of education, or gentlemen who, though well born and bred, grow tired of scientific conversation." I don't choose to say much upon this head. I'm a plain man and in a single station, but, O ye lords and ladies intellectual, pray tell us truly, have they not henpecked you all? Ada's mother was a straight-laced religious bigot. Although very concerned for her daughter's welfare and her morals, she had very little desire to spend time with the child, and entrusted her upbringing to her own mother, the Honourable Lady Milbank. She did not allow Ada to see a portrait of her father until she was 20. When Ada was dying from cancer of the uterus, at the age of 36, her mother refused to allow her to be given opiates to relieve the pain because they would cloud her mind and stop her being truly repentant. Ada herself was somewhat rebellious. Whether this was a trait inherited from her father or a consequence of her upbringing, we can't possibly judge. When she was 17, she tried to elope with one of her tutors. Later in life, some years after she was married, she formed relationships with several men which, while probably innocent enough by modern standards, certainly caused eyebrows to be raised by society at the time. She also became addicted to gambling and accumulated substantial debts before she died. Both of these pictures are true, more or less. But obviously there's a great deal more that could be said. But from the age of 17 onwards, mathematics became Ada's primary intellectual interest, and it was clear that she had great talent. She was tutored by, amongst others, De Morgan. Those of you who know something of mathematical logic or logic design, it's the De Morgan after whom De Morgan's laws are named. And also by Mary Somerville, after whom the first Oxford Women's College was named. It was through Somerville that she first met. How did that come up there? Anyway, it was through Mary Somerville that she first met Charles Babbage when she was still 17. She was to maintain a close intellectual relationship with Babbage for the rest of her life. And it was this, of course, which led to the work for which she is famous. Babbage thought highly of her, so did Michael Faraday and a number of other distinguished scientists. Now, unlike, say, Mary Somerville or Caroline Herschel, whose achievements were recognised in their lifetime, both those two were elected honorary members of the Royal Astronomical Society in 1835, for example. Unlike them, Ada Lovelace's work went unrecognised during her lifetime, as indeed did Babbage's work in the same sort of area, work on the difference engine, the analytical engine. But Babbage did lots of other things. He was a polymath, and his reputation amongst his contemporaries was very considerable, but it came from other things. It didn't come from building computers. As we shall see in the rest of the programme tonight, Ada's work arguably showed more originality than the work of Mary Somerville or Caroline Herschel. But it was ahead of its time, and the technology didn't exist to build the machines which could implement her ideas. It was also, of course, the case that Ada died at the age of 37, and she'd had 3 children by then, so she'd spent comparatively little time on the work for which she is now remembered. All she wrote was a translation of the Italian mathematician Luigi Menabrea's memoir of the analytical engine, which he wrote after hearing Babbage lecture in Turin. Ada translated that of the paper that he wrote, and then put together a set of notes that demonstrated the potential of the machine, including a description of how it could be used to calculate Bernoulli numbers. If anyone doesn't know what Bernoulli numbers are and wants to know, do ask me afterwards. And this was indeed the first computer program, even though the computer to run it did not exist. Right, thank you. Now, Fred.
Thank you, Frank. Our next speaker is Jim, who's going to give us an overview of the engine.
Just point to is up there.
Yes, I'll do it. Right.
Please work. Did you make it in Libre office?
It's fine, I tested it. I say that. So far, so good. Okay, we're going to talk a bit about the analytical engine and then a bit about what Ada realised the analytical engine could do, which nobody else at the time seemed to notice. That is actually an early plan of the engine, and I'll come back to it later. Now, we've already had a little bit of discussion about this chap called Luigi Manabria, who wrote a sketch of the engine and what it could do, based on Babbage's lectures when he visited Turin. That's the chap, that gentleman. Later on, he became the Prime Minister of Italy, believe it or not. I love that picture. Now, a few words about the difference engine. This was Babbage's first machine, which, again, Babbage didn't finish. Some say it's because he got bored, having thought up the analytical engine, but Ada denies this. Ada says that Babbage stopped work on the difference engine some years before, and the analytical engine came out of another train of thought. But there are some similarities. The difference engine was built to calculate log tables. For those of you of some age, you may remember having to use these little books of tables of logs, sines, tangents, and all that before we had calculators. I remember they were just going out as I left school. They were awful things. Your opinion may differ. They were laboriously produced by hand by people who were called calculators. And they were error prone. In fact, Charles Babbage and his friend John Herschel, the astronomer, used to sit up late at night proofreading log tables for fun. How those winter evenings must have just flown by. The method that they used to produce these is called the method of finite differences. It's very, very simple, but I'm not going to go into it in any detail. It approximates polynomials. That's all it does. And it does this just by adding up. And that's all the difference engine was. It was an adding machine. It took a number, added it to a column, which represented another number, a column of gears, added the result of that addition to another column, added the result of that addition to another column, and so on. Every time you wound the crank, and then printed the number out at the end. It was just 7 adding machines linked together. Very, very intricate, but not really that complicated in conception. Ada said about the difference engine, it is the embodying of one particular and very limited set of operations. This adding up, moving to the bottom of the next column, adding up, and so on. Whereas the analytical engine is an embodying of the science of operations, constructed with reference to abstract number. She's talking about it does things. The difference engine does just one thing, the analytic engine does all the things, essentially. Now that's the plan I showed you earlier. I'm going to overlay that with some stuff to break it down into regions. Now I'm going to get rid of the plan because that's confusing matters. These are the main components of the engine. The store stores values in columns, just like the difference engine does. The mill takes two values that somehow come out of the store, does something with them, produces the result. And that will go back in the store. The rack is what transfers information between the mill and the store. That is what a little bit of the store might have looked like if it was actually built. That's actually a close-up of a difference engine that someone's managed to construct. You can see that each column, which represents a single number, is made up of a whole load of gears, each of which is a single digit. That's what the store might have looked like. Back to that. I'm going to move this diagram around now to make its operation a bit more clear. What I've done is I've split the rack into its three sections. There are two so-called ingress racks, which take values out of the store and input them to the mill. And there's an egress rack, which takes data out of the mill and puts it back into the store again. Programming the engine is picking which parts of the store to connect to the mill and then which operation you do. And this is done with strings of cards, inspired by the Jacquard loom, an automated piece of machinery for weaving lace that was invented in France. And here we have some of what those cards might have looked like. There were four kinds of cards. Variable cards, they were going to connect the store and the mill by pushing the right part of the store up against the rack, or vice versa, depending on which design you're looking at. The operation cards, they pick which operation that the mill was going to perform by changing its physical configuration, moving things about. Number cards get constants into the store, so you've got some data to work with in the first place. And combination cards meant that the whole string, because these cards were put on strings, the whole string of cards could be moved backwards and forwards. So you could say something like, if the last result of the mill was a negative number, move the string of cards back 20 spaces. That way you can have loops. You could also jump forward over bits of code. That way you can have conditions. With that, you now have what we call a Turing complete system. It can calculate, Ada wouldn't have realized this, Babbage wouldn't have realized this, Turing only came along over 100 years later and figured it out. It can calculate anything that can be calculated, albeit very, very slowly. It could multiply two 20-digit numbers in 2 minutes, which is thought to be phenomenally fast. Back to this diagram, I'm going to show you just a little example of what some cards might do. So, we have 6 variables in the store. We have a variable card which connects the first ingress rack to variable 2. We have another one that connects the second ingress rack to variable 5. And then we have another one which connects the output to variable 3. And then we have a fourth card which says multiply. That will do the operation V3 becomes V2 times V5. With a whole bunch of cards like that and some combination cards, you've got yourself a computer program. Does this diagram look familiar to anybody in the room? It might do, because it's the design of a modern CPU. Modern processors work exactly that way, pretty much. That is how prescient Babbage's design was. It was very, very clever. These days, instead of cards, we have something called microcode, which is a program that is burnt into the CPU when it's made. When your CPU runs an instruction, it runs a tiny little piece of microcode. No, assembly language is not the lowest level of programming there is. Microcode, if you look at it, is weirdly like analytical engine programming. It's eerie how similar it is. Right, generality. What Ada did in her notes was showed what the analytical engine could do with this power. I'm going to quote from her quite a lot. Hopefully I've got time. Many persons imagine that because the business of the engine is to give its results as numbers, I'm going to be paraphrasing as I read, the nature of its processes must be numerical. In other words, Because it's working on numbers, everything you do with it must be numbers. And she said, this is an error. The engine can arrange and combine its numerical quantities exactly as if they were letters or anything else, or vice versa. The operating mechanism might act on other things besides number. This is kind of obvious to anyone who works in computers today, but it certainly wasn't then. If you read Menandria's sketch and you read Babbage's stuff, they were all thinking entirely in terms of a calculator machine. Really? There were some hints at this. For example, supposing that the fundamental relations of sounds could be expressed in such a way, the engine might compose elaborate and scientific pieces of music. If you can describe the things that you're working with, and you can describe the relationships between them and the operations on them precisely enough, then you can write a program for the analytical engine. It could be anything. It could be music, it could be text, it could be pictures, whatever. That's what she's saying. How could you do this? It must be easy, she said, to bring out a double set of results. First, the numbers that you are really working with. Secondly, the symbols that you attach to those numbers. And we do this all the time in computing. It's encoding. For example, that colour, we use an RGB triplet, 3 numbers, to represent it. So, no red, bit of green, bit of blue. Or music, we use the number 60 to represent the middle C in the musical instrument digital interface, which every piece of hardware, electronic music hardware uses. And ASCII encoding of text, of course. So, she wrote the first program, but yes, she was pretty much the first person to talk about an automatic machine being able to process something other than numbers. And she showed how it might be done by encoding values as numbers. A little postscript. She died in 1852 at the age of 36, very, very young. 2 years later, George Boole published The Laws of Thought, which talks about values that are just true or false and specifies operations like and, or, and not. Things that really are the building blocks of computers as we know them today. It's interesting to think what she might have made out of that. And that's where I stop.
Thank you, Jim. So Clive is now going to talk about memory and reuse.
Okay, now for something all right, I'll do it. So I arrived back in Aberystwyth in about 1991, and I was kind of like a pit bull at the cat show. I was a C programmer and arrived in the department of 4 Ada people. So I'd heard this name, Ada, and I associated it obviously with the language, and I probably did that until about 2 weeks ago when I was asked to do this. And so it's been a bit of a voyage for me, and sort of a bit of a voyage of discovery. And I'm going to kind of make this assertion that if Ada Lovelace was alive today, she would be a C programmer, hacking the Linux kernel, rather than writing Ada code for drones in Aberystwyth. So that's my assertion. I hope you will agree with me. So I work in industry, so I'm completely shameless about things like advertising. This is on in tomorrow. Very good. 8 o'clock. So, search my notes. So, Jim's was one of the things when you have 5 or 6 people and sort of giving talks and they don't come together, and so there's going to be a lot of overlap. So Jim showed us pictures of the difference engine, and each of the numbers written on, they were described in the document as draftsmen, and I kind of had this in my pic when I first read it. I had this picture of either people doing drawing, technical drawing, or people who looked after shire horses, and they said they stacked them very high, large draftsmen. And eventually it sort of clicked that it was the game that you play, 3,000-year-old game you play on a chessboard. One of the interesting things is that I don't believe that an analytical engine has actually been built. They were reading around this. There was a call for money to go and build it. So you just wonder what they could have done with a piece of poly tube and some paper plates. I didn't think Thomas the Tank Engine was. But this is basically memory, and I think you're all right. I'm not going to get, not with this sort of knife. Is that do it here? This may go horribly wrong. I've not tried this. But basically, as Jim, this is basically what memory is. So we see numbers, and it would basically spin round to keep count. And this is how memory was implemented, or in the idea for the difference engine. And there was a stack of these. They're not set the table. What's going to happen? A stack of columns. And so, for example, if we've got 0 here, and 1 there, if we wanted to store the number 24, very simple. But, and we're thinking, how much technology, when we have, my sort of set of microprocessors, most of them are quite old, and how much things have moved on between paper plates and a piece of polypipe, but that it was 200 years ago, you could not build a difference engine that had the ideas, and that was really one of the remarkable things for me. So this was in effect the storehouse, and there would be in the plan, or would have been built, or they could have built it, would have been hundreds of these storing data. So it was called basically the storehouse. The other bit I got from this was these effectively what they called is the columns. Each column was a V for variable. They weren't just variables; they'd also be able to store as constants. So where was I? The other significant part of the inspiration for this, and the other side of it, as Jim mentioned, takes my stole my thunder a bit, but was the jacquard loom. And this actually, I found this in a way more interesting than the analytical engine. And I say about producing lace and having a series of cards that can be run through. And I found this fascinating for the time and the way that it worked in terms of using prisms and running back and forward. It's well worth reading up on. And so just another a number of different implementations of these. The other bit that struck me, and this is perhaps for me the most important thing, is how important the cards were. Is there actually ended up being the first instance of abstraction and able to take away from what was actually going on here, and in terms of being able to reuse the cards. And for me, that was perhaps the biggest leap that Ada was able to make was to identify abstraction, which basically everything we do today is built upon. So what I think is so I'd still like to argue that Ada would be a C programmer. Having to work at such a low level, manipulating the actual objects, I still think she'd be hacking the Linux kernel in the bedroom rather than writing code for drones in Aberystwyth.
Thank you. Now, Hannah is going to talk about order and efficiency, which is ironic.
I've been a bit of an Ada fan for ages, but I've never actually read what she wrote before an embarrassingly short amount of time ago. We decided that we wanted to do something for Ada, and it turns out she'd written just the one thing, which is one of the weirdest things is that it's a translation. Yeah? So she's doing this because she spoke good enough Italian to translate some Italian. French? Was it?
It wasn't French, yeah.
Was it French?
It was Italian, but he wrote
It was Italian. These people, God, weren't they brilliant? Anyway, so there's a number of notes in this, and I got note D, which is order and efficiency. And one of the things that struck me the first time I read it, well, not much struck me the first time I read it, because it's kind of dense, yeah? It's not a straightforward thing to read. But one of the things she really grasped was that there was a lot of complexity in the system. So there are frequently several distinct sets of effects going on simultaneously, or in a manner independent of each other, yet to a greater or lesser degree exercising mutual influence. So this system has got a lot of complexity in it, and the way these things interact, the variable cards and the inputs and the outputs and stores are all really quite intricate. And she really dove down into the detail of how these things worked. So what I'm going to try and do is intersperse quotes from Ada with my attempt at translating that into the kind of things that we talk of now. So she had three types of variable in the machine. There's the data variables, or those on which data is inscribed, in Ada's words. And I think of these as input variables or maybe parameters in modern computer science parlance. There are output variables, return values in modern computer science parlance, which she said those that are intended to receive final results. And then using the wonderful capitalization that she just sort of sticks capital letters in the middle of a sentence, those for intermediate and temporary results, which are sort of working variables. And there are some really weird things about working variables in the analytical engine that I'll go into in a bit more depth. But having come up with this sort of taxonomy of the different types of variables that we can have in this machine, she then makes it all a little bit more complicated still. So results variables sometimes partake of the nature of working variables. I wish I could talk about my code this way. This variable is partaking of the nature. Working variables. I think this is probably like incrementing something in place, yeah? So you've got a results variable, it takes some inputs, and then you do something to the result before it becomes the final result. So this is pseudocode, maybe summing up what this might actually mean. Variables for data often become working variables or result variables. So even these data variables can become other stuff. And I would say this has been modern computer science parlance, maybe like working directly on the input to a function. And it's not clear to me quite how unusual things could possibly get. So there are two different types of variable cards within the machine. And some of their primary use is the same, so they supply a variable. But what happens next differs between the two types of cards. And I can't think of any parallel for this in computer science. I'm sure someone will prove me wrong within 30 seconds. But one of these types of variable will turn to 0 after use. And if you've ever coded in C, it's probably quite useful sometimes to have variables that tidy up after themselves. And the other would cause a variable to return to the original value after use, which is not quite a constant. So it's not that the variable doesn't change, but it returns to its original value after you've done something to it.
It's more like something that's been stacked,
Yeah.
And then you stack them, so name, shadow is first name.
Could be, but these are the same variables. It's really quite complicated. So the use of variables is one thing, but it must be evident how multifarious and how mutually complicated are the considerations which the working of such an engine involve. I think multifarious and mutually complicated is certainly how I felt the first time I read it. But then she introduces these things called upper indices, and it's still, after some 5 or 6 readings, unclear to me whether these indices are actually part of the machine or actually Ada's interpretation of what the machine is doing. And given the machine never existed, I guess that's kind of an academic question, but academic questions are what we're here for, isn't it? So the upper indices are basically, they keep a record of how often a variable has changed and enable you to trace a calculation through the machine. So their office is to indicate any alteration in the value which a variable represents. And I think these enable you to step back through calculations, and whether they're a part of the machine or whether this is Ada's brain interpreting the results of a machine in much the same way that a debugger would interpret the results of a program is something that I'm not quite clear about myself. There are several advantages in having a set of indices of this nature, but these advantages are perhaps hardly of the kind to be immediately perceived, unless by mind somewhat accustomed to trace the successive steps by means of which the engine accomplishes its purposes. And my mind is not that way accustomed, so I shall, she several times she pulls what I think of the Fermat trick, which is, if I had more time, I would explain this more thoroughly. We wish we had enough space to explain this more thoroughly. But these indices are really, it's really interesting to see the way she uses them to trace through a calculation as she's going on. And I'm not sure, but I think this is quite a lot to do with what we would call now optimization or profiling, where you look at the internal working of a program in order to trace how often a particular thing has been used, or how frequently a variable has changed and so on. These are the kind of things that you do when you've got a program that almost works or that works but doesn't quite work quickly enough. And what you're trying to do is turn it into something that's a little bit faster. And it is indeed an interesting and curious question. Unfortunately, she didn't have enough space to explain it. The essential object, though, is to choose that arrangement which will tend to reduce to a minimum the time necessary for completing the calculation. And speaking as someone who's written programs that have taken days to finish, I agree with this principle entirely. In almost every computation, a great variety of arrangements for the succession of processes is possible, and various considerations must influence the selection amongst them for the purposes of a calculating engine. This entire note is about optimization and how you make the best use of the variables you have, and how you trace back through what you've done in order to make things more efficient. So in 5 pages, written over 100 years before anybody had even built a computer, she spoke of variable reuse, inputs and outputs, debugging, optimization, and I think profiling is certainly in there in some sense, and definitely she's got a concern for efficiency. And I'm just quite amazed at the level of detail that she manages to go into on a machine that never even existed. And that's me, Chris.
Thank you. And now Roger is going to talk about looping and cycling.
As Clive has already said, we're going to tread on each other's toes of time here, so I'll probably go through this quite fast because I'm repeating some things. I love BCS events because I get all these stupid letters after the best part of this slide, I think, is one of the pictures of Ada I have not seen before. Girl geek there. This shouldn't frighten many people, the idea of adding things up, and you can see what we're doing here is iterating something, and some might even know the shortcut to the computer, some, but never mind. And I suppose that probably won't frighten you either. That's how we might represent the expression above rather more succinctly. And there's a very short step, I think, to re-represent that as we might when we're telling a computer to do this. Fairly straightforward. So that's quite easy. But that's the breakthrough that she made. Yeah, so she could see how that was going to be very useful and very important. So you've got to think about living in a world where that sort of bottom representation hadn't ever been seen before. So these are, we're all doing this, aren't we? These are the words that she wrote. When she thinks about a computer program, of course, she thinks there's a pile of cards. We've seen pictures of the cards. Secure the possibility of bringing any particular card or set of cards into use any number of times. She's talking about a loop. And laying it on a little more thickly, once it's done duty once, brought back to the position it occupied just before it was used the preceding time. I think Jim explained that really very clearly. This process may obviously be repeated any number of times. This is not for us a terribly difficult thing to get our heads around, but I reiterate, put yourself in 1840. Not many people would have known what on earth this woman was talking about, would they? Because it is clear, if you read the appendices that I was given as homework, that you can see the formula I put on the first slide, but it wasn't very interesting at all. This one's much more interesting, isn't it? We don't know what the function F is, but let's suppose we can compute it somehow, using all those cogs and wheels and party plates and whatever else Clive used to construct his analytical engine. Because when we write it as a piece of computer code, it looks something like that, where we're going to see that F can be minced into this engine somehow. And it may in turn have a loop, mightn't it? And she could see that if you can construct a loop in a computer program, what is to stop you putting a loop within a loop, within a loop, within a loop, within a loop, just as much as you like. And this opens up levels of complexity and computation which presumably nobody had ever thought about doing before because you couldn't. And the potential of this, I think, that she realised the potential of this is quite jaw-dropping. So, I mean, there was nothing new about algebra. You know, people have been using sigma signs and things, or whatever they used in those days, for a long, long time. But to move from the algebra to the idea of a machine doing it, and how the machine might do it, was awesome. So I confess I hadn't done this homework. I'm glad I've done it now. Those among you who did A-level maths or in a mid-life school O-level maths might be able to attach a date to the idea of Taylor series. Fourier, perhaps not to school, not me anyway. But Taylor published in the 18th century and Fourier published in the early part of the 19th century, and she would have known about these results.
The Taylor series was the power difference machine.
So she would have seen, given that you could construct a programmable machine that could loop as intricately as you liked, what the potential of that mathematics might be for the computing things. Of great complexity. And she could also see that if you built something that worked, it could work on anything, on things as big as you like. So this is as hard as the maths get. That's the worst equation I'm going to put up. Many people present know how to solve that and do it by gas elimination. And if you read her words, she tells you exactly how you would do it. And she points out that the actual arithmetic operations to solve that equation are really quite straightforward. But as the matrix gets bigger, so the number of computations goes up really quite fast. But this is certainly for them was a big, big problem. But it's not a problem once you've got a computer program, is it? Because it's the same program. And we know that now. If you write a program that works, it'll probably work again tomorrow and the day after that. But that was an astonishing insight for the time, I think. She didn't, as I think has already been pointed out, stop to consider exactly how long the party plates would have to revolve on the. What were they revolving on, Clive?
Piece of polypipe.
Piece of polypipe.
That's an
But hey, who cares? Who cares when the alternative is rooms full of people with pencil and slate and chalk? Because what people could do in 1850 with pieces of chalk and paper and what have you was pretty much at the limit of what was actually required at the time. And she gives some nice examples of this actually from astronomy, but they could have come from a number of fields. And it really wasn't difficult to find things that people wanted to do that they wouldn't try to do because it was beyond the ability of the people with their chalk and blackboards. And very often the results of interest were handed out to half a dozen people who of course came back with half a dozen completely different answers because it was just too difficult to get it right. That's before you got into experimental considerations. Problem goes away once you've built a machine. And that's a lovely one, isn't it? Those are her words. Not necessarily that something we're doing has ever been done before. Put yourself back in 1840 and realise how revolutionary that comment is. I think that's really smart, and it certainly wasn't 1840. So, my bottom line is the foresight she showed, having got hold of this very simple idea of a loop. So thinking up new things, thinking up the idea of an analytical engine, hats off to Babbage, yeah? It's tough, but it's always very interesting to see how the new ideas, the new developments are actually used when you let them loose. And there's a couple of examples there that you might like to toy with. But she managed to work out how this machine would be used, even though it never actually got built. I think that's one step beyond, but that's another picture I haven't seen before. But there you go. Go again. I'll pass on to Amanda.
Finally, Amanda is going to talk about limitations and discoveries and also draw some conclusions.
So, the sketch of the analytical engine, you can download the Ada Lovelace Wikipedia page has a link to it. So, I recommend if you want to find out more about Ada afterwards, you download it and you can just read it. And what happened was this Italian officer of the military engineers, he was asked by Babbage to write something about the machine because basically Babbage needed to raise money to fund the building of this machine. So he wanted a document from someone else that said, this is a great machine, how useful it is to the world's community, please fund this machine. And so this guy wrote a document. And at the time, Babbage had managed to acquire £17,500 for the difference engine, which is quite a lot of money today, but it was a massive amount of money back then. It was worth about £60 million. Imagine for a research project, £60 million. It could have bought 2 battleships at the time, and instead they spent it on the difference engine. So now he was trying to build an analytical engine, another machine which would cost more money again, and he needed some way of raising the money for this. And so this getting somebody to write what it did was part of that process. And this guy wrote about what it did. And then Ada decided to translate it, and she wrote to Babbage. There's a whole series of letters that are still kept. She wrote to Babbage and says, I'm going to translate it. And he was surprised. And he said, oh, that's nice. But you knew so much about the machine. Why didn't you just write your own? And she said at the time, well, I didn't think of that. But that was common for women back then. They were in their place and they weren't expected to think that they could be the one to write such a document that would sell to the government. That was normal. So instead, she translated it, and Babbage encouraged her to add her own notes. And then it wouldn't be hers as such, it would be notes by the translator, and that's how it's come about. It's notes by the translator. And Babbage said he would help her out with Note G, which is the one I'm going to talk about, which includes the program. But it's definitely the case that she did some of the work in Note G as well as the rest of the notes. So Note G. Note G is where she starts to get really philosophical about the possibilities for such a machine. And this is again where I think she diverges completely from the original material. The original material by an officer of the military engineers is kind of what you'd expect. It's a description of the machine works like this, it does that, it can produce that, and that's a great thing. Whereas when you read Ada's notes, they're all, this is fantastic, this can do this, she's really visionary about what it might do in the future. And she gets to know G, and she's built up, this is fantastic so much. And she starts to bring people back down and say, while we're at it, don't get too carried away. The analytical engine has no pretensions whatever to originate anything. It can do whatever we know how to order it to perform. So she's saying it's not intelligent yet. She's sort of almost realizing that artificial intelligence might come with it. She's seeing the scope of the machine. She's wanting to reassure the public it's not going to take over the world. She says this is what it does do. She decides that at this point she better make a list of what it actually does do and just reassure everyone it does basic calculations and algebraic calculation, not just arithmetic, but it performs the 4 operations of simple arithmetic on any numbers whatever. Point 2 is about that there's no limit to the magnitude of the numbers used or to the number of quantities that can be used as well, how many variables and so on. It can combine these numbers and these quantities either algebraically or arithmetically in relations unlimited as to variety, extent or complexity. It uses signs as well, it uses algebraic signs, so we can do plus and minus and logical consequences and so on. It can arbitrarily substitute any formula for any other. And it can provide for singular values, which is talking about zeros and infinities, difficult to represent things in machines. So here's what it does do. Don't worry about it too much. This is the sort of thing it does do. And then she starts to warn the people who are reading this document a bit more as well. And by the way, be a bit careful. It is desirable to guard against the possibility of exaggerated ideas that might arise as to the powers of the analytical engine. And she goes on to say, we should be careful about overrating what it can do. And this is what's happened in computing ever since. People have built up hype about what computers are going to do for the world, and then it hasn't happened, and people got disappointed and so on. But also, be careful about undervaluing it as well. Don't lose sight of what it actually does do and how worthy that is. It can follow analysis, but it has no power of anticipating any analytical relations object. It can't make things up, it can't have intuition, it's not magic. It's just going to do what we tell it to do. And she was realizing at the time that what Babbage really wanted was money from the government. So what she was really writing here was a sales pitch for him. And this is what I've been missing so far. In fact, this sort of don't worry, it's not going to be intelligent kind of line of thought Turing picked up on in 1950, 100 years later, when he wrote his classic paper about AI. And that paper is also worth reading if you haven't read it yet. But in this paper, Turing goes through a whole load of possible objections people might raise to the idea of artificial intelligence, of machines becoming intelligent in themselves. And number 6 out of, I think there's 9 or 10, number 6 is Lady Lovelace's objection. So he's read her work and he brings it up and says, our most detailed information of Babbage's analytical engine comes from a memoir by Lady Lovelace. In it, she states that the analytical engine has no pretensions to originate anything. It can do whatever we know how to order it to perform. Another picture of the cards. I just want to put back in your heads what she was thinking of at the time when she was writing this whole document. There was no machine. She was imagining how it would work and what it would do. And yet she's imagining the capabilities and the limitations of the machine as well. This was one of the programs that is expressed in the original document that she translated. And this is a program to look at solving simultaneous equations. So here's the 2 simultaneous equations down here. We've got x and y as our variables, and the equation says that mx plus ny equals d. And then we've got some other constants, m prime x and n prime y equals d prime. So what does x equal and what does d equal? Well, we can find out these things by this formula. And once we've got this formula, we can calculate it in a program. And this is the kind of thing that she would have thought about writing as a program. So these are the operations that are going to happen. The first thing we're going to do is multiply, and we're going to multiply variable 2 with variable 4 and produce variable 8. And that will give us dn prime, and so on. So you list out the operations that are going to be performed, and then this is going to be the results at the end. And these columns are going to receive the results. And the program then that she goes into in her notes, partly or possibly all written by Babbage, but this is the program in note G. Looks like this. This is why she has the name as being the first programmer, because this program was the first one really written for a computer. This is not just a translation of a mathematical thing that you would write out, but she would have had to think, how would we implement it on this machine, and how could we describe it? And I don't know if you can see, there's a sort of gap. It's a very tiny writing down here. It says, there follows a repetition of operations, I think it's something like 11 through 23. So this is the looping stage, which is left by a gap. She's not going to express the loop here, but show this can be calculated. And this program, as Frank started by saying, is to calculate the Bernoulli numbers. And he's kindly offered to explain the Bernoulli numbers to anybody that wants at the end. But basically, they are a sequence of numbers, rational numbers, numbers with decimal places. And these numbers crop up again and again in number theory and solving various things, such as the expansions of formulae that were designed to calculate things like the tangent of an angle. So this was that. And in this discussion of this algorithm here, she talks about how complicated it was. Back to Hannah's point about order and efficiency. So she discusses what's going on in terms of how many cards it's going to use, how many variables it's going to use, how it's going to work. And she does a discussion of what lines of the operation are going to do. So number 6 there is about taking the negative of a number by subtracting it from 0, and so on. So this line does this, and this line does that. And this, note G is mostly a discussion about how this algorithm works. And although Babbage said he would write a lot of note G to help her out because she had a lot to do to translate all of this stuff in 9 months, it's clear that she had a big hand in it because she wrote to him in her letters things like this. I have yesterday evening and this morning very amply analysed the question of the number of variable cards as mentioned in the final note H or G. She can't even remember what note we're up to now, or maybe they moved the notes around, but it was note G. And I find that you and I, between us, have made a mess of it. Her italics on the word mess, for which I can perfectly account in a very natural manner. I enclose what I wish to insert instead of that which is there. So she's obviously gone over it again. And this is wrong, it shouldn't work like that, it should work like this. So I'll just close with Ada Lovelace. She died at the age of 36, the same age as her poet father, Byron, some years ago, some years before her. You can find the sketch of the analytical engine online, which was published in 1842. She was 27 years old then, you can imagine. And it's written as if it's a sketch of the analytical engine with notes by Ada Augusta, or Augusta Ada, Countess of Lovelace. So, yeah, I just think she's amazing. I'll leave it there. One more quote that I forgot to say. In note A, she discusses the science of operations. Jim mentioned that. Her quote reads like this: but the science of operations, and she's talking about operations that the machine can do, the science of operations, as derived from mathematics especially, is a science of itself and has its own abstract truth and value. We have to wonder, is she talking about computer science there, the science of operations, this new science that is derived from mathematics and has its own abstraction?
Right, thank you. That was fascinating. Please can we thank all of our speakers again. perhaps if some members of the committee, we're supposed to have it in the little, what's called the conservatory opposite, for health and safety reasons, which I don't really understand. So the book way will be set up. This is just opposite here. Can I point out our next meeting is a week today in room C22, which is that building and sort of further up. And that's Rob Clark talking about security in the cloud. And then we also have 2 meetings in November on the 13th and 27th of November. Both of those are Thursdays, and those meetings are back in this room. Thank you all for coming, and I hope you enjoyed the buffet.